Namaskar. Today we will look into the various aspects of volcanic eruptions under the following headings. Number 1, the occurrence and distribution of volcanoes, the products and hazards associated with volcanic eruptions, the prediction and mitigation of volcanoes, the history of volcanic eruptions, and the use of volcanic products. We begin with the distribution of volcanoes. Volcanoes have always been a part of the Earth's long history. Volcanoes, or the evidence of volcanoes, has been located almost everywhere on the Earth's surface. Ancient lava flows that have been found in many places where there are no volcanoes today, and most of the deep ocean floors are made up of thick layers of volcano underneath much of the thinner layers of sediment. Most volcanoes are located near the edges of continents. The geological theory of plate tectonics helps explain this. According to the theory of plate tectonics, the Earth's crust consists of several huge plates or blocks that move slowly around the planet. As these crustal plates move, they frequently collide. This melted rock then rises as magma, forming volcanoes near where the plates meet. Along the edges of the Pacific Ocean, the huge Pacific plate is sliding under a number of continental plates. The areas along this large arc is called the Ring of Fire because many active volcanoes are found along it. Other arcs of active volcanoes run through Italy, Greece, Turkey, Armenia, and Indonesia. Volcanoes are also located where plates are spreading apart. When this happens, magma pushes up between the plates and creates volcanic activity. Scientists have discovered this type of volcanic activity in the Atlantic Ocean along the Mid-Atlantic Ridge, which is an undersea mountain range that marks the boundary between huge spreading plates. Iceland's volcanoes are found along this volcanic ridge. A number of volcanoes also occur along the Rift Valley of Eastern Africa, another region where crustal plates are spreading apart. While most volcanoes form where crustal plates are, as the plate above a hotspot moves, the fixed column of magma continues to form new volcanoes. The Hawaiian Islands, the most famous mid-plate volcanoes, are a good example of this process. Each island was formed one at a time over a hotspot. As the plate above the hotspot moved, a new volcano and a new island was formed. The youngest island, the Big Island of Hawaii, is now above the hotspot, and this is where Hawaii's active volcanoes are located. Now let us look at the products of volcanoes. There are three types of volcanic products identified, namely lava flows, tephra, and volcanic gases. Lava is the liquid product that is extruded from any type of volcano, but there are different types of lavas. Only low viscosity lava tends to flow very far from the crater. Tephra, also called pyroclastic debris, refers to the fragments of volcanic rock and lava that are blasted into the air during eruptions. Tephra includes a wide range in particle sizes ranging from ash to bombs and blocks. Volcanic gases. These gases propel volcanic eruptions and are also emitted from volcanoes either during an eruption of lava and ash or as a separate eruption of gas. Now let us look at the hazardous phenomena associated with volcanoes. Volcanoes can be exciting and fascinating, but also very dangerous. Any kind of volcano is capable of creating harmful or deadly phenomena, whether during an eruption or during a period of quiescence. Understanding what a volcano can do is the first step in mitigating volcanic hazards. But it is important to remember that even if scientists have studied a volcano for decades, they do not necessarily know everything it is capable of. Several hazardous phenomena are associated directly with volcanic eruptions. They are ground fracture, ground subsidence, debris avalanche, lahars, glacier bursts, volcanic earthquakes, and tsunamis. Volcanologists are always working to understand how volcanic hazards behave and what can be done to avoid them. The various types of volcanic hazards and their characteristics are as follows. Number 1, lava flows. Lava flows are less dangerous to human life than to property, traffic, and communication because the probable path of lava flows can roughly be predicted. Mitigation measures include cooling the advancing front of lava with water or disruption of a source or advancing front of lava flow by explosives. However, such measures often turn out to not to be very successful. Highly viscous lava generally does not advance far, but commonly piles up above an active volcanic vent as a lava dome. Such domes can collapse repeatedly and generate dangerous hot block and ash flows and hot surges and blasts. Number 2, poisonous and even toxic gases can be ejected during the eruption of a volcano or can be released without a triggering eruption. The gases are transported away from the vent as acid aerosols, as compounds absorbed on pyroclastic material, and as microscopic salt particles. Sulfur compounds, chlorine and fluorine react with water to form poisonous acids damaging to the eyes, skin and respiratory system of animals, even in small concentrations. Most volcanic gases are harmful and smell bad and can cause mass fatalities. The time available for early warning or gas release is extremely short, and intensified investigation on such gas eruption as well as keen observation of the respective locations is absolutely necessary. Number 3, ashfalls. Ashfalls during volcanic eruption generally do not directly endanger life, although the collapse of roof and houses under the ash load are not uncommon. Considerable damage may be caused, however, for agriculture and industry even at distances up to tens of kilometers from a volcanic vent. Many of the hazards of ash falls can be mitigated with proper planning and preparation, which includes clearing ash from roofs as it accumulates, designing roofs with steep slopes, strengthening roofs and walls, designing filters for machinery, wearing respiratory or wet clothes over the mouth and nose. Number 4, pyroclastic flows. Pyroclastic flows are frequently associated with blasts and are extremely hazardous types of volcanic eruptions. Pyroclastic flows consist of a mixture of volcanic gases and ash and are generated during many volcanic eruptions. Some may be as hot as 900 degrees centigrade. They move swiftly with velocities up to several hundreds of kilometers per second. Early warning for this volcanic phenomena is virtually impossible. The only effective method of risk mitigation is evacuation prior to such eruption from areas likely to be affected by pyroclastic flows. Number 5, lahars. These are also referred to as volcanic mud and debris flow. These are common major volcanic hazards for people and property. Lahars proceed very quickly and possess great destructive power. They develop either as a direct consequence of a volcanic eruption of crater blowout or as a secondary event following heavy rainfall during or after volcanic eruption. Areas farther away may be warned several hours in advance. Small lahars can be diverted by barriers or by artificial channels which lead them away from the valuable land or property. But in most cases, the volume and force of lahar is such that it is beyond human power to control. Number 6, volcanic debris. Volcanic debris avalanches generated by sliding of large portions of volcanic cones are common. These avalanches are highly mobile and may not only bury large tracts of land but also cause devastating tidal waves or tsunamis if they advance into lakes or the sea. The only effective method of risk management is evacuation prior to such debris avalanche or tsunamis from areas likely to be affected by this kind of phenomenon. The secondary phenomena associated with volcanic eruptions include tsunamis, contaminated ashes, or long-lasting aerosol clouds that can orbit the earth for years after volcanic eruptions. Then aerosol clouds basically consist of condensed volcanic gases, mainly sulfuric acid. The emission of large quantities of sulfur dioxide and possible halogens into the stratosphere may lead to a temperature decrease on the Earth's surface by increasing the global albedo, and also can contribute significantly to the destruction of the stratospheric ozone layer. If sulfur-based aerosols reach the upper atmosphere, they can block sunlight and interfere with ozone, which have both short and long-term effects on climate. Now let us look at the predictions of volcanic eruptions. The development of methods to predict volcanic eruptions is extremely important to provide for early evacuation of densely populated regions. Hazard and risk potential of volcanoes can be localized reasonably well, unlike some other natural disasters like earthquakes and storms. Reliable predictions to a minimum degree, however, are only possible for volcanoes that are well studied and sufficiently monitored instrumentally. A prediction based on the statistics of previous eruptions is too vague for specific and short-term prediction of an eruption. A forecast is a general announcement that a volcano will probably erupt in the near future, example by qualitative signs of unrest. A prediction is a relatively precise statement that describes the part of a volcano that is likely to erupt, the time of eruption, and the presumable type of eruption. Such predictions must be made public with utmost caution in order to gain credibility within the concerned population, thus enabling adoption of preparedness measures. A careful analysis of the history of a volcano is the most important method in assessing the long-term probability of occurrence of a specific eruption type and its eruptive energy. Volcanic eruptions are often announced years, months, days, or hours before. Example, by harmonic tremors in the deeper conduit system. This microseismic activity commonly increases prior to an eruption and is characterized by relatively constant amplitudes and wavelengths that are possibly caused by the turbulent motion of the magma ascending to the surface from a magma chamber. The relatively slow ascent of viscous magma to the upper crust generates a surface expansion that can be measured with modern geodetic instruments. Temperature increases within a volcano as a result of ascending magma, which can be detected by infrared signals via satellite. Heat conductivity and the magnetic fields are changing prior to volcanic eruptions. An increase of sulfur dioxide emission often has been observed before volcanic eruptions. In addition to ground-based monitoring, scientists now use satellites and satellite technology to track volcanoes. Satellites provide information that traditional methods cannot. For example, sensors on satellites can detect the warming of volcanoes, sometimes even before they erupt. Sensors can also measure the amount of gases given off during eruptions. For volcanoes in remote areas, satellite monitoring may be the only method available. Now let us discuss the prevention and mitigation of volcanic hazards. To prevent future disasters, or at least to reduce their extent, a series of measures must be taken before, during, and after a volcanic eruption. Various regional research centers, especially in Latin America and Southeast Asia, should be established that have archives containing all relevant methods and can serve as centers for training for volcanologists, for public education, and for cooperation with other scientific institutions. The preparation of hazard maps helps to determine whether a volcano is potentially hazardous and to assess the risk. For that purpose, detailed knowledge about the history and characteristic of specific volcano is indispensable, which requires, among other things, topographic and geological mapping. Hazard maps show the pathways of eruption products to be expected, such as lava flows or pyroclastic flows for various eruption intensities. Monitoring of volcanoes by satellites has to increase in order to detect possible changes like temperature or sulfur dioxide emission. Continuous monitoring is essential. When a volcano has been identified as potentially dangerous, ground monitoring, both visual and instrumental, should be ensured. The public must be informed and educated on the results of volcanological studies and possible dangers. For potentially dangerous volcanic regions, emergency plans must be worked out, particularly evacuation plans for the population in case of immediate danger. Disaster prevention exercises, such as already carried out in Japan, are useful as well. A volcanic eruption cannot be influenced by man. There are, however, limited possibilities to controlling several of its effects, such as barriers against lava flows or cooling lava with seawater. Smaller lahars can be channeled by artificial dams. Long-term regional planning can significantly reduce the hazard potential. Disaster reduction measures can contribute to mitigate the impact of volcanic eruptions. Fatalities and economic losses can be reduced if associated with a well monitoring system, including early warning and land use planning. More than 500 million people live within the potential exposure range of a volcano. The risk of catastrophic losses in future eruptions is significant, given that population growth, proximity of major cities to volcanoes, and the possibility of larger eruptions. There were a total of 91,789 deaths, 14,068 injuries, and 4.72 million people affected by volcanic events between 1900 and 2008. Changes in land use practices and population growth provide a background for increasing risk. From a global disaster perspective, volcanic eruptions result in relatively little mortality and displacement. By comparison, floods were the leading cause of death in the 20th century. At present, there are an estimated 550 active volcanoes, many of which are in locations experiencing rapid population growth. Many urban centers are commonly found within close proximity to volcanoes, including Naples and the capital cities of Mexico, Japan, and the Philippines. Population density generally decreases as distance from the volcano increases, with the highest population densities in close proximity to volcanoes in parts of Southeast Asia and Central America. The risk of catastrophic loss from future eruptions is significant given population growth, proximity of major cities to volcanoes, and the possibility of larger eruptions. Now let us look at the history of volcanic activity. Some of the volcanoes located in India are the Bharatang Island in the Bay of Bengal, the Barren Islands, and the Narko Dam, which is an island in the Bay of Bengal. The Barren Island erupted in 2013 and it is a stratotype of volcano. 10 of the largest volcanoes of the world are the Mount Mazama or the Crater Lake in Oregon, which erupted over 6,000 years ago. Number 2, Mount Etna in Sicily is the highest active volcano in Europe. Number 3, Mount Vesuvius in Italy, which erupted in 79 AD, which covered the cities of Pompeii and Herculaneum, preserving them for generations to come. Number 4 is Mount Tambora in Indonesia, the largest eruption during the last 2 centuries as well as the deadliest volcanoes in recorded history. Mount Tambora exploded April 10 to 11, 1815 and killed an estimated 92,000 people. The eruption and the resulting massive clouds of dust and ash affected most of the northern hemisphere, causing unusually cool temperatures and failed crops in 1816. Number 5 is Mount Krakatau in Indonesia. On August 27, 1883, it exploded with such force that it was heard in Australia over 2,000 miles away. The force of the eruption triggered a series of tsunamis that reached the Hawaiian Islands and the coast of South America, killing more than 36,000 people. Number 6 is Mount Pelée in Martinique, which erupted on May 8, 1902 and killed 29,000 people. Number 7 is Paricutin in Mexico, which erupted in 1943 and resulted in a pile of ash which covered cornfield near the town of Paricutin, Mexico. A mountain began to emerge from the earth, reaching a height of 1,200 feet in 1 year due to this volcano. Number 8 is Mount St. Helens in Washington, one of the most highly publicized and studied volcanic explosions. This mountain erupted on May 18, 1980. The volcano, which had been dormant since 1857, began erupting steam after a series of earthquakes in March 1980. Number 9 is Nevada del Ruiz in Colombia. Although the eruption occurred on November 13, 1985, it was relatively small. The ensuing mudslides caused by the melting ice and snow resulted in the death of 23,000 people and the destruction of the town of Armero. Number 10 is Mount Pinatubo in Philippines, which erupted in June 1991. It was 10 times larger than Mount St. Helens eruption and one of the biggest of the 20th century, killing almost 800 and leaving an estimated 100,000 homeless. The next section is Volcanic Explosivity Index. The Volcanic Explosivity Index, VEI for short, was devised in 1982 to provide a relative measure of the explosiveness of volcanic eruptions. Chris Newhall of the United States Geological Survey and Stephen Self of the University of Hawaii developed the Volcanic Explosivity Index. It is a relative scale that enables explosive volcanic eruptions to be compared with one another. It is very valuable because it can be used for both recent volcanic eruptions that scientists have witnessed and historic eruptions that happened thousands to millions of years ago. Volume of products, eruption cloud height, and qualitative observations are used to determine the explosivity value. The scale is open-ended, with the largest volcanoes in history given magnitude 8. A value of 0 is given for non-explosive eruptions defined as less than 10,000 cubic meters of tephra ejected. 8 represents a mega colossal explosive eruption that can eject 10 to the power of 12 cubic meter of tephra and have a cloud column height of over 50 km. The scale is logarithmic, with each interval on the scale representing a 10-fold increase in observed ejecta. A total of 47 eruptions of VEI 8 magnitude or above, ranging in age from Ordovician to Pleistocene, have been identified, of which 42 occurred in the past 36 million years. The most recent is Lake Taupo eruption 26,500 years ago, which means that there have not been any Holocene eruptions with a VEI of 8. Now let us look at the benefits of volcanoes. Volcanoes are windows to the Earth's interior and reveal information about the interior of the Earth. Volcanic activity is the ultimate source of valuable natural resources. Many valuable mineral deposits are found in the roots of extinct volcanoes. Solid debris erupted from volcanoes such as pumice and ash are useful as construction materials and abrasives. Towering cone-shaped volcanoes such as Mount Fuji in Japan are tourist centers. Snow-covered volcanic slopes are ski resorts. Geothermal springs in volcanically active areas are used as spas. Volcanic ash and lava transform into fertile soil that supports vegetation and